This is a video presentation of a model of time, part 2. The focus will be on atomic time. We argued in the Hubble constant paper and presentation that the universe is a surface volume of an expanding 4D hypersphere called the hyperverse. Its radius is expanding at twice the speed of light, and its circumference is expanding at a rate equal to the Hubble constant. A visual might help. The hyperverse is expanding at 2 times the speed of light, 2c. The surface is three-dimensional, and the increase in the surface matches the Hubble constant. This idea is particularly important. The Hubble constant is a measure of the rate of separation of galaxies. Our calculated increase in the circumference based on the hyperverse model matches the Hubble constant. Additionally, we developed an equation that says that the Hubble constant is a measure of the addition of energy to the universe. This implies that space exists. It is not a vacuum. Space exists as energy. This is what it should be, as the surface volume has to be different from the nothingness into which it is expanding. If the hyperverse surface volume, which is our universe, exists as energy, we can then inquire into the nature of its structure. Based on the information given in this paper and the future papers, we will claim that the surface volume of the hyperverse is composed of miniature 4D vortices. The vortices spin, and their energy is related to their spin, and they all have the same energy. Let's look at the energy of the atoms of space that comprise the surface volume of the hyperverse. We're going to claim that the sum of the potential energy and the linear kinetic energy is equal to a constant, mc squared. The L stands for linear, which we will use as a replacement for translational motion, because we're going to reserve the T for tangential. The equation for linear kinetic energy is 1/2 mv sub L squared. M stands for mass. Since all vortices spin, they all possess rotational kinetic energy. The equation for that is 1/2 I omega squared. I is the moment of inertia, and omega stands for the angular velocity. We will define the rotational kinetic energy as the potential energy of the unit of space. It will be displayed as Ke sub r. There's an interesting observation. We find that the square root of the net potential energy equals the special relativity time function, and we're going to spend a little time working on this. The Lorentz factor is given by this term. We're going to use this particular notation. The Lorentz factor is the time dilation factor of special relativity. The inverse of the Lorentz factor is given by this, and this is what we're referring to when we talk about the special relativity time function. We've already defined that the potential energy and the linear kinetic energy is equal to a constant. Rearranging, we find that potential energy is equal to the total energy minus the linear kinetic energy. We know the linear kinetic energy is given by this term, so we find the potential energy is equal to the total energy minus this. We will define the net potential energy as the potential energy minus the kinetic energy. Doing a little algebra, we find that the net potential energy is equal to the total energy minus 2 times the linear kinetic energy. We'll take the square root of each side. We're going to say c is 1 and m is 1. This makes this 1, and this v sub L squared. And this is what we defined as a special relativity time function. We can make a graph. Velocity, energy. We find that the linear kinetic energy follows this curve here. This spot represents the speed of light. We're going to add the curve now for the potential energy. The sum of the linear kinetic energy and the rotational kinetic energy comes to a constant. Now if we take the potential energy and subtract from it the linear kinetic energy, we find this new plot here, which is the potential energy minus the linear kinetic energy. In this image, we've added the square root of the potential energy minus the linear kinetic energy. The square root of this line here gives us this particular curve here. Let us now calculate the tangential velocity of the vortex. Tangential velocity, or v sub t, is the rim speed along any particular point on the surface of a rotating circle. In trying to find out what v sub t is, we take our equation for the rotational kinetic energy, plug in our values for the moment of inertia and omega squared. we find that the rotational kinetic energy is equal to 1/2 times the mass times the tangential velocity squared. We know the rotational kinetic energy and the linear kinetic energy, and we know that the sum of the potential and kinetic energies are a constant at mc squared. Doing the math, we find that the tangential velocity is equal to the square root of 2c squared minus the linear velocity squared. We've seen that the tangential velocity is given by this term. If the linear velocity is 0, we find that the tangential velocity is equal to the square root of 2c squared, which comes the square root of 2 times c. If the linear velocity is c, we find 2c squared minus c, take the square root, and we find that tangential velocity is equal to c. So the tangential velocity ranges from the square root of 2c to c as velocity goes from 0 to the speed of light. With a tangential velocity equal to the square root of 2 times c, it gives us a possible concern. And answering this concern actually adds support for the 2c radial expansion concept. And this is the question: is the tangential velocity of the square root of 2 times c, which is greater than the speed of light, is that a violation of relativity? Let's ask a question. If a car is going down a highway, the speed limit is 50 miles per hour, and a traffic cop is there watching, can you get a speeding ticket if you're going 50 miles an hour? Well, no, because your car is not moving translationally down the highway at a speed greater than 50 miles per hour. But there is a spot in your car moving at 100 miles per hour. It's the top of your tires. So is that a violation of the speed limit? Let's look at this. We have the tire moving translationally at 50 miles per hour. Top of the tire has a translational motion of 50 miles per hour, plus a rotational motion that adds to it of 50 miles an hour, giving a total of 100 miles per hour. The bottom of the tire has a velocity of 0. It's at instantaneous rest. Okay, in our model, we have our spinning atom of space. In this particular case, the linear velocity is 0. There is no translational motion. We find that v sub t, or the tangential velocity at all points, equals the square root of 2 times c. In the case where the translational motion v sub l is equal to the speed of light, we know that tangential velocity also equals the speed of light. The sum of the linear velocity and the tangential velocity, both equal to c, comes to 2c. Note that the maximum velocity here on this spinning atom of space is 2 times the speed of light. We find that c, the speed of light, is the maximum translational velocity in the universe. The maximum rotational velocity is the square root of 2 times c when the object is at rest. And we find that 2c is the maximum combined translational and rotational velocity, which is very interesting because this matches the radial expansion rate. It appears the expansion of space sets the speed limit in the universe. We've seen that the square root of the net rotational kinetic energy gives us the special relativity time function. Equivalently, the net potential energy is equal to the square of the relativistic time function. Let's look at a very revealing way to picture the energies. Let's look at a specific example. If the vortex is moving translationally at half the speed of light, or v sub l is equal to 0.5 c, we find the tangential velocity is equal to the square root of 1.75 times c, or approximately 1.323 times c. We're going to kind of draw a picture. Velocity on both sides. What we have here is 0.5 c, this is the linear velocity, and here is the square root of 1.75 times c, and that's the tangential velocity. We've got these points matched up. So we make a little square here for the linear velocity and a little square here for the tangential velocity. We're going to take our velocity squares from the last picture. Linear velocity, 0.5 c, made a square here, but energy is equal to 1/2 mass times the velocity squared. We're going to consider the mass equal to 1, so the energy is 1/2 of the velocity squared. So the square we had here, taking 1/2 of it, gives us a triangle here. The same idea goes for the rotational kinetic energy. We had our energy square, the translational velocity squared, If we take 1/2 of that, we get this blue triangle. This represents the rotational kinetic energy. And we had said before that if we take the rotational kinetic energy and subtract from it the linear kinetic energy, we get the net potential energy. We've seen this red triangle here as linear kinetic energy, and that equation is 1/2 mv sub L squared. Our potential energy, or rotational kinetic energy, is given by 1/2 times mass times the tangential velocity squared. The green area here looks like it might be an energy. If it is, we could say that the kinetic energy of time would be equal to 1/2 times mass times v sub c squared. The question, is there a third energy? Is there an energy related to time? This particular picture implies there may be. We can calculate the velocity of this possible third energy. Doing some algebra, we work our way down and we find that the velocity would be equal to the square root of 2c squared minus 2 times the linear velocity squared. Very interestingly, our three velocities form a right triangle. Using our velocity values for the 0.5 c example, we have our linear velocity, our tangential velocity, and this new velocity we calculated. The three velocities always form a right triangle. Ultimately, we find a Pythagorean theorem relationship where the linear velocity squared plus v sub c squared, the velocity connected to time, is equal to the tangential velocity squared. We'll look at a couple of examples. In this one, with the linear velocity equal to 0.1 times the speed of light, we find the linear kinetic energy as this little tiny triangle down here. Our rotational or potential energy triangle is here, and our energy related to time is huge. Taking the velocities from these points, we find this particular triangle. And on the other extreme, with linear velocity equal to 0.9 c, we find the linear kinetic energy has grown quite a bit, and the time-related energy is shrinking. It gives us a triangle shown here, and we find that as the velocity continues to increase, the height of this triangle drops down and down and down. And ultimately, the tangential velocity and linear velocities will become equal. We see a clear relationship between the energies and the velocities, and there's a reason for it. The new energy and velocity are resultant values. And let's explain that. If an object is moving with a velocity in this direction, and there's force coming from the side, we find that you add the vectors and we have a resultant direction. So if a ball is thrown this way and the wind is blowing this way, the ball is going to move along this particular path. This is the resultant value. Now we're going to start on centripetal velocity. We're going to show that this resultant velocity is the centripetal velocity. Centripetal velocity is a center-seeking velocity. And we need to spend a little time on it because this particular topic is hardly spoken of at all in physics texts. Centripetal velocity is not the same thing as tangential velocity. Let's look at a spinning object that is not moving relative to us. Its linear velocity is equal to 0. The tangential velocity we know to be the square root of 2 times c, and this applies to all points along the circumference. The force connected with this tangential velocity points towards the center of the circle. Let's look at the situation where the spinning atom of space is moving with a linear velocity of 1/2 the speed of light. This vector here represents this. All points along this circle are moving to the right at 0.5 c. We have a tangential velocity, which we calculate out to be the square root of 1.75 times c. We add that velocity here, and we're going to come down to the bottom, and it goes the other way, so that the net motion is given here. Looking further at our circle moving with a linear velocity of 0.5 c, we know its tangential velocity is the square root of 1.75 times c. We connect the tip of this vector combination and this net vector here. Where it crosses the midline here, this point here, is the instant center of rotation. We're going to call this the IC. Looking at our circle moving to the right with a linear velocity of 0.5 c, we have the center of the circle, and the linear velocity has forced the center of rotation, the instant center of rotation, to drop. If we go from the true center of the circle to this point on the perimeter and take the tangential velocity to it, we find this line here. We know our linear velocity is here, and we sum the two, and we get this resultant vector. If we go from the instant center of rotation to a point on the perimeter of the circle, and we take the tangent vector to that instant center's point of rotation, we get the same vector that we got here. So the resultant vector from our true center and the linear velocity matches exactly the tangent vector for the instant center of rotation. So we can say that v sub c is the vector that's tangent not to the center of the circle, but to the instant center of rotation. So looking at our three vectors, linear velocity is given here, tangential velocity is here, and the centripetal velocity vector is here. The tangential velocity vector is tangent to the center of the circle, but the centripetal velocity vector is tangent to the instant center of rotation. As the linear velocity increases, the instant center of rotation drops lower and lower until it reaches the bottom. At this point, we have achieved a light speed, and the object would appear to roll, and a point on the surface would trace a cycloid curve. Looking at a picture of this, we find that the linear velocity would be equal to c, the tangential velocity would be equal to c, given a total of 2c, and the instant center of rotation would be at the bottom. Tangential velocity is the same as centripetal velocity, only when the object is at rest relative to the observer, when v sub l is equal to 0. Let's compare the equations for the tangential and centripetal velocities. We know that the tangential velocity is the square root of 2c squared minus the linear velocity squared, whereas the centripetal velocity is the square root of 2c squared minus 2 times the linear velocity squared. Graphing those two equations, we find the tangential velocity and the centripetal velocity start the same and diverge as linear velocity increases. This point is the speed of light. Centripetal velocity is very important because it's related to the period of time it takes a spinning object to complete a revolution. V sub c, the centripetal velocity, is equal to the circumference of the circle divided by the period of rotation. We find that if v sub c drops, that the period increases, so as v sub c approaches 0, the period will approach infinity. Frequency is the inverse of period. It would be given by the centripetal velocity divided by 2 pi r. We know that v sub c is this value here, so we can say the frequency is given by this term. We measure time with our own frequency. We're at rest. Our frequency is the base frequency. Our linear velocity is 0. Doing the math tells us that our base frequency would be the square root of 2c divided by 2 pi r. We're going to take the ratio of the observed frequency to the base frequency. Doing the math gives us this term here, which is the inverse of the Lorentz factor. So we have seen that the ratio of the observed to the base frequency is equal to the inverse of the Lorentz factor. We can rearrange this, and we find that we get the time dilation equation from special relativity, where this term here is our stationary clock time, that's the base frequency. This term here is the moving clock time, that's the observed frequency, and this is the Lorentz factor. So we just derived the special relativity time dilation equation, and we did it using the vortices of space that this model postulates comprises the surface volume of the hyperverse. Atomic time is determined by the frequency of rotation of the atoms of space. This, in combination with the concept of hyperverse time given in Part 1, we can explain everything from the arrow of time to relativity. Matter is made of the vortices of space, as we will show in the paper on matter. The descriptions given here for the atoms of space, or vortices or quanta, as discussed in the geometric mean paper, apply to matter, as matter is condensed space, forced to collapse to conserve the angular momentum of the expanding hyperverse surface volume. And we will see that the equations of matter give us gravity.